Well, hello everyone. Last time we started talking about noise in some analog modulation systems and their detectors, that is demodulators. Specifically, we studied double sideband suppressed carrier as well as SSB. Today we continue with conventional AM with envelope detection. So as you know very well, the receiver front end is often modeled as adding Gaussian noise onto the incoming signal, and we have an equivalent filter that stands for all the filtering effects of the RF front end. Now, in the case of conventional AM, this is followed by an envelope detector. So let's see the contribution of the envelope detector to the noise, all right, or how it handles the noise. First of all, we're going to compute a baseband SNR like we did for the other modulation types. Oh, let me just make sure that I pin this video. One moment. Okay, so now the incoming signal is conventional AM, hence it can be expressed as AC 1 plus Ka M of T cosine WCT, where of course for the envelope detector to work, Ka M of T has to be less than 1 in magnitude. And we're assuming, like we do usually, a zero DC signal. All right, so the signal power can be computed by computing the autocorrelation function evaluated at 0, which is essentially, in this case, the expectation of signal squared, which gives us AC squared times a half 1 plus Ka squared PM. As you can see, it's different from SSB and double sideband in the sense that we have this Ka squared term multiplying the message power. This is the main reason for the power inefficiency that we discussed actually from the start when we introduced conventional AM for the first time. Now we'll see the numerical effect of this inefficiency in terms of SNR. Now, how about the baseband noise? We've been through the computation for this many times. As you know, we're multiplying n naught over 2 by 2W. And as a result, it gives us n naught W. Okay, so the SNRB is then computed as AC squared 1 plus Ka squared PM over 2 n naught W. Okay, so how about noise? Now, let's go through the noise computations. The message bandwidth is W. Okay. Note that this refers to the one-sided bandwidth. Of course, HR of F, when you think about the ideal HR of F, it has bandwidth 2W around FC. So the bandpass noise has a spectrum that looks just like this. Okay, so we're talking about the bandpass noise having PSD equal to n naught over 2 in a passband of 2W, size 2W in positive and negative frequencies. So as a result, the noise power is equal to 2 n naught W. This is the passband. We're talking about passband noise or bandpass noise. Bandpass noise. Okay. Now, as we argued last time, the in-phase component and the quadrature component of the noise also have the same power. Now, let's think about our passband signal as it exits HR of F. I mean, as it exits the front-end filter. Our signal X of t is filtered signal plus filtered noise, okay? And it's a passband signal. So it's going to have AC 1 plus KAM of t plus NI of t times cosine minus NQ of t sine WCT. Why? Why? Because we're talking about this signal here. Oops. Plus the bandpass noise, which is Ni of t, the in-phase component of the noise, times cosine WCT plus NQ of t sine WCT. And as a result, we're going to have this term. Okay. So we can always think about this after the envelope detector. We can always think about the envelope, provided it correctly goes through the envelope detector and the envelope is detected. The expression for the envelope is, of course, the square root of the cosine magnitude squared plus the sine magnitude squared. Okay. So now this is the time in order to find the output SNR on this y of t. We're going to apply some approximations because, as you can see, it is highly nonlinear. So the main approximation is the high SNR assumption. Okay, which is going to be necessary for the envelope detector to work anyway. Okay, so the assumption is that the noise is not as bad as to be significant over the power of the signal. The noise should not dominate. Okay, so what does that mean? The signal term is much stronger compared to the noise term, such that the first term in this expression is much larger than the second, which means, of course, then we can then ignore the second, the additive term inside the square root, and then get rid of the square root. When we get rid of the square root, we end up with y of t being approximately AC 1 plus KM of t plus additive noise. So we just showed that provided the SNR is strong enough, the output of the envelope detector has additive noise. But we know how to compute SNR when there is additive noise. And so with this, we are now in business. We can just compute. We could have computed SNR from here, but there's a further approximation step. We're saying, well, if the SNR is that high, the signal power must be high. So why not get rid of this one, which we could. You might as well not do it, but in the textbook, in many standard computations, in the high SNR limit, we do get rid of that one. And okay, so, oh, one moment. This is after the DC blocking, so I take that back. That's because of the DC blocking, because we're trying to, detect the signal. So that's why the DC blocking takes care of the one, and we're left with only the time varying component of the signal in which our message lies. Okay, we don't want to be reading our signal on top of DC. We're blocking the DC and letting our signal appear. So, okay, this is the actual output, not Y of t. So Z of t is the demodulator output. So we are going to compute the SNR from Z of t. So compute this correlation at 0 as AC squared KA squared PM. And the noise power is simply the power of the in-phase noise, which we already computed as 2 and not W. Remember why it's 2 and not W? Because it's bandpass noise with PSD and not over 2. Okay. This is 2W here, hence it's 2 and not W. Okay. So the output SNR is then signal out divided by noise out, which gives us this expression. What was the baseband expression? The baseband expression was AC squared 1 plus KA squared PM over 2 and not W. And this is AC squared KA squared PM over 2 and not W. So the 2 and not W's cancel. And we have KA squared PM divided by 1 plus KA squared PM. Okay. So in order for the figure of merit to approximate 1, you would need KA to be very large, right? So in order for the efficiency of the system to be maximized, you want KA to be large, but then there's a trade-off, because if KA is too large, there's a problem. The envelope detector will stop working. Okay. So then there is a design trade-off between choosing KA large for power efficiency and choosing KA small enough for easy detection. Okay. Now let's consider the low SNR case. Let's see what's going to go wrong in the low SNR case. Again, we can express our bandpass noise as before. And we can think about it is in terms of its amplitude, time varying amplitude, and the time varying phase. Okay. Now, we can think about the cosine and the negative sign as two dimensions, and I and Q can be thought of as the magnitudes of two vectors lying on those orthogonal dimensions. Okay, so this is the usual phasor notation that we made use of before in this course too. So the amplitude, time varying amplitude, is the square root of Ni squared plus Nq squared. The tangent of the angle is the ratio of Nq by Ni. So now we're going to see in the low SNR limits, we will see the addition of this noise on top of the time varying signal, and what happens. So here is our signal. And I'm adding noise on top of it. Okay. Now here is the NQ and NI as before. The noise components have been drawn in the red, and they are large, a little bit exaggerated to show that noise is large. This is a low signal to noise ratio limit, remember? And my signal is here, the black vector that's aligned with the in-phase noise, of course, is my signal component. Okay, it is smaller with respect to noise. So let's see what happens. If the signal is small enough, then this theta x angle is essentially going to be dominated by the angle of the bandpass noise. This is the angle of the noise. In other words, phase. Okay. This is the resultant angle. This is theta x. And when this component is small enough, when signal is small enough, this angle can be approximated by this angle. Of course, I mean, in the limit and the low SNR limit, essentially. And then we will be able to go further with this analysis using this assumption. Now we've replaced cosine theta x. So basically, what is AX of t? AX of t. AX of t is the resulting, so basically the magnitude of the blue vector here. Okay, so you obtain that by squaring AC1 plus KAM of t plus NI plus squaring NQ and then taking the square root, right? However, now we can approximate that as AC1 plus KAM of t times cosine phi n plus AN of t. Right? Why? Because of this approximation between the two angles. Okay. So now AN of t is the magnitude of the noise. So when you express y of t in terms of AN and cosine phi n, we see that there's additive noise, but there's also multiplicative noise, and that is a problem. Okay. Now NQ and NI, as they are Gaussian, they are also independent. Okay. And tangent theta n is the ratio of NQ to NI. Okay, since they're independent Gaussians, okay, this angle theta n is going to be uniformly distributed in 0 to 2 pi. So it is going to completely blur the signal. This is going to cause message loss because the cosine takes equally, I mean, phi n takes equally likely values from negative pi to pi. So that means the cosine term is going to randomly attenuate our message, therefore resulting in irreparable loss. Okay, so this loss of the message in an envelope detector that operates at low baseband SNR is referred to as the threshold effect for SNR. When does the threshold effect occur? Well, we didn't say really anything about, and I don't think anybody can really pinpoint to a particular value, but when, let's see, when this no longer holds, when the baseband SNR, or in other words, the carrier to noise ratio is not significantly larger than 1. I mean, of course, you start getting to the, you start getting to poor performance, and after a while, you totally lost the signal. So here is a example curve in dB scale of SNR O over SNRC, which is the figure of merit. SNRC stands for SNRB. Sometimes in some textbooks, since it's the carrier to noise ratio, it's also abbreviated as SNRC. So if you plot this, okay, and you'll see so roughly a position for the threshold. By threshold, we mean a value of the carrier to noise ratio below which the noise performance starts deteriorating rapidly. So I don't know, pick a location. For example, after this point, decay is faster. Once the decay becomes fast, it's only going to be faster. So that's why it's called the threshold effect. Let's do an example. Suppose we have a message signal which has 10 kilohertz bandwidth. Okay, so W is 10 kilohertz, and the power is 0.5 watts. Okay, this message is transmitted over a channel where N naught is e to the minus 20 watt per hertz. Find the required receiver power in order to achieve output SNR bigger than 40 dB. Okay, for double sideband, single sideband, conventional AM with modulation index 0.8. First of all, whatever we find for double sideband, SSP is going to be similar because and we don't have to do an extra computation, essentially, because they have the same figure of merit. So first of all, compute the SNRB. SNRB is the message signal power divided by the noise power in the message bandwidth, remember? So we're talking about N naught over 2, and this is 2W. So N naught W. Okay. So SNRB is whatever is the power in the received signal divided by N naught W, which is 10 to the minus 20 watt per hertz times W, which is 10 to the 4 hertz. 10 to the 4, because 10 kilohertz. Okay, so it's 10 to the 16 times the received power. this received signal power. Now we're going to compute what the received signal power should be in order for us to achieve this output SNR. Now for double sideband and single sideband, output SNR is equal to the baseband SNR. So since output SNR is required to be bigger than 40 dB, input SNR is required to be bigger than 40 dB. That is, the lowest power acceptable, lowest SNR acceptable is 10 to the 4. 40 dB is 10 to the 4. Why? Because 10 log 10 to the 4 is 40. Okay, the dB computation that we do in EE 435 and in communication in general is 10 log SNR, okay, or 10 log power. Okay, sometimes in electronics you use 20, right? But here you're going to use 10, okay, because we're talking about units of power, and power is in general a second order value with respect to things like voltage, for example. Okay, so now what did we find? We found that 10 to the 6 times PR should be equal to 10 to the 4. Okay, so PR is 10 to the 4 divided by 10 to the 6, 10 to the negative 12. So 1 picowatt is enough to satisfy this. So what do you think? I mean, it is surprising. It doesn't sound practical to transmit 1 picowatt. I mean, that is to receive 1 picowatt and still have output SNR 40 dB. Well, with the given noise and with the given bandwidth, remember, we're talking about very narrow band communication here. And the message power being very large. Okay. So it turns out to be like this. Okay. Now for conventional AM, SNRO is figure of merit times SNRB, and figure of merit is like this. For Ka squared equal to 0.64, coming from the 0.8 Ka, okay, we find that this is 0.24 times SNRB. So the efficiency is like, the figure of merit is like 25, less than 25%. Okay. So we need roughly 4 times as much transmit power. Okay. And turns out to be exactly 4.16 picowatt transmit power. Any questions? Okay, so that's all about amplitude modulation. I'll stop the recording here.